All right, today we are doing 1.6 two-dimensional figures. All right, so our objectives are we're going to identify curves, simple curves, and closed curves. We're going to identify convex and concave regions of a shape, identify and name some circles, polygons, and related terms, and calculate the perimeter of a polygon and circumference of a circle. So hopefully a lot of review for you today. All right, first of all, curves are a continuous set of points. Okay, so technically by this definition, a line is a curve, right? It's just a continuous set of points. It's two-dimensional. So all of these things, A, B, C, and D, are curves. But technically a straight line would be two. Okay, now we have closed curves. These end at the same point where they began. Okay, that's a closed curve. So C is closed curve. Actually, and so is D. So I'll just draw arrows to both of those. Okay, C and D are both closed because they end at the same place. Simple curves never cross. Okay, so this one is simple. This is a simple curve. And C is also a simple curve. D, however, is not because they cross right here. And B, they cross in several places. So that's not simple. Now then, a circle, okay, is a set of all points. So it's always all points in a plane that are a given distance from a point or the circle's center. Okay, so C is technically not a circle because we can't see that it's a given distance from the point. We could say it's a closed curve. We could maybe call it an oval. We cannot call it a circle yet. All right, and then the radius is any segment, so any segment from the center to a point on the circle. So like if I have my circle, it's only a circle because I say it is, and here's my center, right, that's my radius. My board is a little off today, I apologize for that. Might have to recalibrate it here. That's a radius. Any of those from the center out is considered a radius. Okay, good. All right, I'm going to clear this so we can move on. Oh, sorry. Got to change my pointer as well so I can scroll down. I forget about that sometimes. All right, so in example 1, can a curve be classified as the following? Or sorry, can a circle be classified as the following? So, can a circle be a curve? Yes, and we've got to think about those definitions. Okay, a curve is a continuous set of points. I'm going to use PTS for points. So yeah, a curve is just a continuous set of points. A circle is definitely that. Okay, simple. Can it be simple? Remember the definition of simple was that they never cross. So yeah, a circle is also simple because it never crosses. Okay, never cross. How about closed? Remember the definition of closed? They end at the same point they started with. So yes, a circle is closed too, because it ends at same point, PT, it started. So definitely. So a circle is a curve, it's simple, and it's closed. So we might call it a simple closed curve, if you want to put those all together. Okay, next up, some more info here. Let me change up colors a bit. A circle divides a plane into 3 disjoint sets. I hope you're catching on that everything divides stuff into 3 parts. Okay, so there's the points on the circle, so really the circle itself, the points interior, and the points exterior of the circle. Okay, but this is also true of any simple closed curve. So if I were to look at this, okay, here, so 1 is the points on the circle. So the circle itself, any of those points are one set. Then I have the interior. So I have all the points inside is the third part, and all the points exterior are the third point, or the third part of the disjoint set. All right. So now we have this definition of region. Okay. The region is the union of a simple closed curve and its interior. Okay, so the curve is the region's boundary. So when we're talking about a region, the region is, okay, the simple closed curve and its interior. So if we're talking about a circular region, we're talking about the curve and the interior. That's the region. Okay, so when we're unioning those two things together. All right, so another thing, any set of points can be classified as concave or convex. It's a classification that we use. Convex is a little bit harder to kind of wrap your head around the definition, but it says, if every segment with endpoints in the set is completely contained by the set, then it's convex. Okay, that's a little hard to kind of wrap your head around, I know. So sometimes I just look at the definition of concave. So it says if a segment can be drawn whose endpoints are in the set, but the segment is not completely contained by the set. Or in other words, we say the shape caves in, then it's concave. Okay, so this one is concave. And what it's talking about is drawing those endpoints. So like if I drew a point from A to B, that line is not completely in the shape. So it's concave. It's just if it caves in somewhere. So if we look at example, oh, hold on, let me get to the definition of polygon first. Then we can do example 2. So polygon is a simple closed curve. Again, the definition of curve is just that continuous set of points. I know we think of a line all the time, but it's a simple closed curve that is made of only line segments, where each segment is a side and each endpoint is a vertex. Now that's important. So segments are sides, okay? Endpoints are vertexes, or vertices we would actually say in the plural. So in example 2, determine whether each figure is a polygon. Okay, so this first one, my timer's kind of on it, so hopefully you can see the pentagon okay. So is this a polygon? All right, well, it's simple closed curve. It's made of only line segments. So yes, so we would say closed and simple. I would have usually write simple closed curve. And then I have line segments. We're checking that definition. That's some terrible handwriting there. That does say segments, just got all wonky. B, is this a polygon? No, right? We have this curve here. That curve is not a line segment. C, okay, we have the star shape. Is it a polygon? Yes, absolutely it's a polygon. Okay, again, it's a simple closed curve and it has made up of only line segments. D, okay, so D has 1, 2, 3, 4, 5, 6 sides to it. Is it a polygon? No, it is not closed, right? That's an issue. It is not a simple closed curve. It's open right there. So it is not a polygon. All right, let's clear again and move down. Okay, you will notice over here we have all these classifying polygons, these names, and let's see, I'll leave that up there so we'll have it to help us. I don't want to lose those. Now, some more vocabulary. All right, so let's pay close attention to this vocabulary. We have an equilateral polygon. Okay, so that's all the sides are the same length. Okay, equilateral, all the sides are the same length. Then we have equiangular. All the angles are the same measure, the same size. Then we have a regular polygon. And you're like, well, that doesn't say equal anything. But it's super important for you to realize if it says, like if you're reading and it tells you something is a regular polygon, all the angles are the same and all the sides are the same. Okay, that is huge. Okay, so if we go ahead and look down here, and I know that's going to give it away, that's what these tick marks are, right? It's saying, hey, this side is equal to this side. They all have a mark on them that shows us those are equal sides. And then they also have a mark, one curve. Again, I'm sorry that my board's a little off. All these curves are saying that each of those angles is the same. That looks really messy. So I'm just going to erase it and leave it with what's naturally there. How about that? Okay, but that's what those marks mean. Is that the angles, those angles that have those marks are the same, and the sides that have those ticks are the same. So in example 3, we want to classify each polygon by its number of sides, then state whether it forms a concave or convex region. Remember, the region is the outline of the shape, so the curve and its interior, and whether it's equilateral, equiangular, regular, or none of these. So there's a lot there. Let's look at this first one. So it's number of sides. We have 1, 2, 3, 4, 5, 6, 7 sides. So if you don't know, you can look at the chart. That is a heptagon. All right, then is it concave or convex? Well, does it cave in anywhere? Yeah, right, it caves in right here. So this is concave. And is it equilateral, equiangular, regular, or none? Well, we do have some equilateral sides, right? Like there's a tick mark. There's one mark on each of those sides. So it is equilateral. Now, is it equiangular? Notice that this has one curve, right? These angles all have one, but these have two curves. So this angle is congruent to this angle, but they're not all the same. So it's not equiangular, and therefore it cannot be regular. Okay, let's look at B then. So B has 1, 2, 3, 4 sides, which makes it a quadrilateral. So it's a quadrilateral. I may have to erase this too so I can get the rest of my writing in there. Okay, now if you look at the marks here on the side links, it has, oh, I'm sorry, we're doing concave or convex. Does it cave in anywhere? No, that would make it convex then. If there's no caving in, then it's convex. And the last one, equilateral, equiangular, regular, or none. So notice it does have marks, but this side has one mark, this side has two marks, this side has three, and this side has four. So the sides, each side is a different length, it's telling us. Kind of like with the angles. This angle has one curve, this one has two. This angle has three curves, this angle has four curves. It's telling us that none of those angles are equal because they don't have the same number of curves on them. Like if we go back to example A, the ones that just had the one curve for the angle, those were all four congruent. And then the ones that had two curves, those two were congruent with each other. So B here is none. There's no congruent angles, no congruent sides. All right, let's look at C. Okay, so C has 1, 2, 3, 4, 5, 6, 7, 8 sides. An 8-sided polygon is an octagon. Very good. All right, is it concave or convex? Does anything cave in? Nope, so it's convex. All right, and is it equilateral, equiangular, or none? So again, let's look at these little red tick marks, and there's one mark on every side, which means it's equilateral. Okay, so we have equilateral. Then we need to check equiangular. So it has one circle, or one curve, one arc for each angle. Each one is a 1, so that means, hey, it's equiangular as well. All right, and if it is both equilateral and equiangular, that means it is regular. right? Because it's both equilateral and equiangular. So it is regular. You don't have to write regular over that. I'm just saying, like, if it's both of those things, then it is regular. That's just a little helpful maybe. All right, I'm going to clear this and we're going to go on to the back side. All right, so now we're looking at naming. Okay, so polygons are named by listing the vertices in consecutive order. All right, so you might be ABC or 1, 2, 3, but you're going to order them. You can list them clockwise or counterclockwise. It can be CBA as well. Does not matter, but whatever you pick, go in clockwise rotation for where you start. Okay, a diagonal is any segment of a polygon that connects two non-consecutive vertices. All right, so like here, BE is a diagonal, and BD are diagonals. So can you find 3 more diagonals, and how would you name them? Okay, so B, we went to E, we went to D, so we're done with this side, because if we go to A, that's consecutive. If we go to C, that's consecutive, and it has to be non-consecutive. So if we go to A, we could go from A to C and call it segment AC. Okay. You could also call it segment CA. Doesn't matter to me. So I'm going to put, so AC or CA is 1. Let's find another one. All right, we could do AD. So segment AD, make sure you put the segment line over it. Or how else could we name that? Perfect, we could call it segment DA. So segment DA. And we're supposed to find 3. So one more. One more. How about CE? So we've got segment CE, or we could name that what? Perfect, EC. We could name it EC as well. So yeah, any of those. So even though it might look like there's 6 more, the way that we have written them, we drew them out to see that there is only 1, 2, 3 more. There's just 2 ways to name each one. All right, so now we want to find the vertex or angle of a triangle. Oh, sorry. Each vertex or angle of a triangle has a corresponding opposite side. So a vertex or an angle has an opposite side. That's pretty cool. So the side opposite of A, so the side opposite of this angle A is segment BC. Okay, because it's right across from it. So what is the side opposite of angle B? So B, opposite of B is going to be, excellent, segment AC. So we're going to say is segment AC. And then how about opposite of angle C? So angle C is here. We go opposite. That's going to give us segment AB. So every vertex or every angle has an opposite side. Okay, I'm going to go ahead and clear this so we can move up and have a little room for our theorem and our problem. So theorem 1.6.1. So something about these theorems, okay, is they start off 1.6. This is in chapter 1.6. It's in section 6. Okay, so 1.6. And then 0.1, it's the first theorem that you're taught in this section. Okay, so everyone will be like that. So if you are struggling with understanding a theorem and you need to go back and reference it, you can always go off the name of it. Because like down here we have theorem 1.6.2. It's the second one in section 1.6. So, all right, so let's look at this theorem 1.6.1. The perimeter P, so perimeter of a regular n-gon, so this means any size polygon, with sides of length s, so the sides of length s can be found using the formula P equals NS. So notice, N here equals the number of sides, okay, and S equals the side length. This will always, always work. This formula will always, always work for a regular n-gon, the perimeter of a regular n-gon. And P, hopefully you recognize, P stands for perimeter. All right, so in example 4, we're supposed to find the perimeter. Well, is this a regular polygon? No, definitely not. So to find perimeter, we just add up the 3 sides. Okay, so P is going to be side 1 plus side 2 plus side 3, because they're all 3 different. So our perimeter is going to equal 4 plus 8 plus 10. So the perimeter is equal to 22, and we need to throw on our unit of measurement, so 22 centimeters. Great. Now, if we look at this other one in polygon B, notice it says that our side length here is 9, 9, 9, 9, 9. So it is a regular polygon. So I could solve it the same way using this, side 1 plus side 2 plus side 3 plus side 4 plus side 5. Or I can just say that P is equal to N times S, which is P is equal to the number of sides, there are 5 of them, times the side length. The side length is S. Sorry, is 9. It is S here, but it's actually 9 in the polygon. So our perimeter is 5 times 9, which is 45. We don't have a measurement, right? We don't have our unit of measurement, so we would just say 45 units, because we don't know what the unit is. It could be feet, it could be meters, it could be millimeters, it could be yards. So we just say 45 units. But practice trying to use that formula when you have a regular polygon. Okay, next up, we're going to look at some parts of a circle. Okay, so first of all, we have a chord. It's any segments whose endpoints are on the circle. Okay, so if I look here, B has an endpoint on the circle, and so does C. So BC is a chord. D is an endpoint on the circle. A is an endpoint on the circle, so B to A is a chord. So let's do this first one as chords. Diameter then is a chord, so it has to have an endpoint on the circle that contains the center. So the only one that goes, so the center is O, and the only one that has endpoints on the circle and goes through the center is DA. So this is the diameter. All right, so the diameter is a special type of chord. Okay, then we have an arc. An arc is a curve that's a subset of the circle. Okay, and it tells us AE is an arc. So AE is an arc, but so is BD. BD is an arc. And DE is an arc. And BC is an arc. And let's see, CA is an arc. Or we could say AD, or let's see, AB, all the way around there. AB is an arc. So many of these, okay? So it's just any subset of the circle is considered an arc. So let's label these arcs. So arcs are on the outside. So now we've talked about chords, radius, arc. We talked about diameter above, or a radius above, I'm sorry. So remember, like, just from the center to the edge would be the radius. So those are terms that you already know. Okay, I'm going to clean this up, and we're going to move on. Okay, theorem 1.6.2 then is the circumference C. Okay, so you do need to memorize all these formulas. Okay, So the circumference of a circle with a diameter d can be found using these formulas. C equals pi times diameter, or C equals 2 pi times the radius. I'm going to change my color up. Okay, so either of those, depending on the information you're given. So in example 4, we're going to find each missing measure. All right, well here, the r is missing, and we have the circumference, but we still need to use this formula. But notice we're given the radius, so which formula should we use? The one with the radius, right? So we're going to say, okay, well, C equals 2 times pi times r. We're going to use that formula. Our C is 10, so 10 equals 2 pi times r. We can divide by 2 on both sides. So 5 equals pi times r, right? And we're going to leave pi in there, okay? Like we don't have to replace it with 3.14 or anything like that. So now we can just divide by pi. I left it to the end so our answer would look a little nicer. So we divide by pi, and that gives us 5 divided by pi equals r, our radius. And it's in centimeters. So we want to throw that in there too. So 5 over pi centimeters is the radius. It's not the cleanest looking answer, but you're going to get a lot of those in geometry. Okay, we're going to leave the pi in there, and you do that a lot, pretty much all the time. Once you start doing it in algebra, you just leave it in geometry and algebra 2 as well. Let's look at B. The circumference of a water tower that measures 60 feet across. Okay, well, if we're going 60 feet across, that across is what? Is it the diameter or is it the radius? All the way across is a diameter. Okay, and we're talking about this water tower. So now, let's change it up. We're going to use this new formula. C equals pi times d. This time we know our diameter is 60, so we are finding C. So C equals pi times 60. All right, I'm just going to leave the pi in there, right? So I'm just going to rewrite this to where we put the numeral first. And so 60 Earth's circumference equals 60 pi and feet. There you have it. And then that's it. Like 60 pi feet is your answer. Okay. All right. All that's left there is for the on your own for you to have ready for class to check in and see how you're doing. And I'll see you in class.